if you are basically considering any kind of nuclear reaction, in this example we are talking about fission, it's more or less probabilistic in nature. Okay, what do I mean by probabilistic? It means that whenever uranium 236, okay, whenever a uranium 236 breaks into two, it's not necessary that it will be barium or krypton. That is something which we have seen a number of times. Whenever we are looking into a nuclear reactor, then also we do say that yeah, most of the time we observe that this is barium and krypton, and then there are three neutrons which is basically coming out of it, right? And then in a nuclear reactor, we know that we need to control these three neutrons so that the reaction is within control. Okay, otherwise there might be a nuclear explosion, which is also possible. Okay, so but then if you go into the real picture, okay, it's that uranium 236 may break into two, and there might be any two elements. So the probable elements which are possible in a nuclear fission reaction are mostly xenon and strontium. Okay, so you see you basically have two neutrons here, not three neutrons. Okay, and if you add up the atomic number here, 140 plus 94, the mass number, sorry, okay, we have got 140 plus 94, so that would be 234 and plus 2 neutrons, so it is 236, right? So similarly for barium also 139, barium and krypton is 94, so it will be 3 more left, so that will be the 3 neutron which comes out, right? It can also be cesium and rubidium. Okay, so that is also possible, and then you get two neutrons, and then there is also a possibility of iodine and yttrium. Okay, so iodine is 137, yttrium is 97, and then you again have got two neutrons which is basically coming out of it. So these are some of the reactions or some of the fissionable materials that will actually some of the fissioned material. Okay, now, so basically when uranium 236 fissions, you might get any of these combinations. Okay, possibility. So if we basically plot a graph between yield, what do I mean by yield? In yield in generally, you can say that this is basically a probability. Okay, the probability of getting a nuclei after fission of uranium 236, okay, can be plotted. And then if we plot it with respect to the mass number, okay, for the fragments, it was seen that most of the times, okay, see, this is the highest probability here, this is the highest probability here, most of the times the fission fragment will have a mass number of either 95 and 140 combination. Okay, so if you look into this 95 and 140, you look into these values here, 140, this is 139, 141, 137, all is in the vicinity of 140, near to 140. And look into the other component, 94, 94, 95, 97. So this is near this value of 95. So if you look into the probabilistic picture, okay, we do have these two elements which are coming out, and these two elements will more or less have the mass number near 95 and 140. But the example that we have looked into when we talked about fission, and we said that if we have a nuclei having A greater than 100, we will have fission. And later on, we did observe that it should be greater than 300 for having spontaneous fission. In both the cases, we considered that the nuclei will break up into two, okay, equal parts. That means both of them will have the same mass number, 118. So if you consider 236 and it breaks into two, you can have two mass number which is equal to 118, 118. But you see the probability is very low here compared to these higher probabilities. So the chances of having elements, okay, fission fragments, which are basically having a value of 95 and 140 is more. And that's the reason that whenever a fission reaction happens, you basically get two elements, and both of them will have a mass number near about these. Okay, so you know this is a more or less probabilistic in nature. Okay, so that's what I've written here. So maximum probability for 140 and 95 or nearby. Okay, and number of nuclei into two equal parts will actually be minimum. Okay, so 118, 118, the chances is very less. The maximum chances are for 95 and 140. So to remember that. Okay, and there are also some man-made nuclear materials, okay, but let's anyway not discuss that. Okay? But there are man-made materials also, nuclear materials, which are actually experimented with for, let's say, spontaneous fission or trying to get fissionable material of our own choice and so on. Okay, but in order to have a nuclear reactor up and running, uranium-235 is fine, and then we can actually have a nuclear reactor working fine. Okay, so this is something which we are going to study now, nuclear fission reactor. So the basics, I think all of us know about nuclear fission reactor. Should not be very complicated. Okay, we have studied these things before. The diagram is also there, but I'll explain the diagram later. Let's just look into something more basic. We have got something which is called the probability of reaction. So whenever I represent something like sigma, if you remember, we have done it, okay, or we have written as the d sigma by d omega, right? D sigma by d omega. So these actually represent the probability of a reaction happening. So if you remember from your second unit, when we talked about nuclear cross section, the more the cross section, the chances of reaction are more. If the cross section is low, we can say that the chances of reaction is less. Okay, so the probability of reaction will usually decrease, okay, with the increase in neutron energy. What does this mean? I think this is something which you already know. If you are having a very fast neutron hitting the nuclei, okay, or let's say the uranium target, okay, the chances of this affecting a nuclear reaction will be difficult, okay, because it does not have sufficient time to interact. This is something which we discussed when we talked about compound reaction and direct reaction. So here we are more or less interested for a compound reaction and not a direct reaction. Not interested for scattering. We are interested for having a reaction happening. Okay. For that we use something which we call as the moderator, if you remember. So moderator might be graphite or heavy water. Heavy water is mostly used. So what happens is, even if a neutron is coming out at a very fast speed and you want to slow it down further, you can use some heavy water there. And if you can use heavy water, what happens is this will actually slow down the neutron. If it slows down the neutron, the chances of that neutron interacting with the uranium will be far greater. As a result, you can expect that there is a nuclear reaction. Then you can get those two fragments, three more neutrons coming out of it, energy coming out of it, and so on. Okay. So in nuclear physics term, we say this as probability of reaction. In simple words, we are talking about the cross section. Okay. So we basically have something which we call as thermal neutrons, and this will not induce nuclear fission in uranium-238. So you understand now, because the chances of the activation energy is high. So the chances of nuclear uranium-238 after becoming uranium-239 to fission into two separate fragments are less. Okay, so thermal neutrons usually does not induce nuclear fission reaction, but here when we are talking about a nuclear reactor, we are using thermal neutrons. Okay? So what happens is uranium-235 and uranium both can absorb neutron. So how do we know that? Because we have seen it before and we have also seen what is the Q value. Okay, but then uranium-238 and uranium-35 both can absorb neutron, but still there might not be any fission possible, because depending on what energy the neutron is getting incident on uranium, you might have something which we call as the radiative capture. So it will capture the neutron and it won't go into the excited state, or it won't get enough Q value to actually break into two parts. So that is also a possibility, and that is why having the energy of an incoming neutron at a fixed rate is very important. Okay, so this is more or less controlled in those nuclear reactors. Okay, and there is also a possibility that if the neutron does not have slow motion, okay, if it is fast, there might be an elastic or inelastic scattering also, and that is not the aim. Okay, and that is why nuclear reactors are designed in a specific way. So if you look into those high-end nuclear reactors which are being there, okay, and if you've already heard about the Chernobyl disaster and all, these are all uh, uh, related to nuclear reactors. Okay, and there is some certain specific designs of nuclear reactors that usually works. So just have a look at one of the common things. Okay, it's not as simple as it looks, but we are just going to look into it. Okay, so if you have basically a nuclear reactor, the first thing that is important is the fuel. Okay, so let's imagine this, that the fuel that we are talking about is uranium. Okay, and then mostly it's uranium 235. So it is uranium 235. So I have the fuel as uranium 235. What is my next job? My next job is to make neutron incident on it. This is already you studied, so I'm just going to kind of revise it. Okay, just a revision. So we have neutrons, so we can actually have some neutrons which is coming and getting incident. Now you know you need to slow down the neutrons further, okay, so that it reacts with the uranium rod, okay. So what you can do is you can use some moderator, and we can use heavy water, okay. So you know if you're considering something like detergent water or all, these are all nothing but heavy water. So these heavy water can actually slow down the neutrons. As a result, the neutron will actually react with the uranium rod. But then what happens is, if you're considering any of the above reactions that I've shown you, all of these cases, you might have two neutrons or three neutrons, okay, or three neutrons. Now, which is not helpful, because if we are having more neutrons, this will set up a chain reaction, okay. So from 3 neutron, it will become 3 into 3, 9, then it will become 27 and so on. Okay, so we already know it. So what I need to do is, I need to cut down. Okay, so if I have got 2 neutrons, I want to cut down 1 neutron. Okay, so in order to cut down that neutron, we usually call something which we call as the control rod. Okay, so a control rod, there are of course elements, but then most of the time the element that is used is cadmium. Okay, but let me tell you, in this lecture, the aim is not to understand nuclear reactor. The aim is to understand something else. But then if we don't touch the basic, we cannot go forward. So that's why we're doing this. Okay, then this also generates some kind of heat. So there is a water jacket, okay, some coolant which is flowing, okay, depends on how much heat it generates. Depending on that, the system is designed, and that coolant flows around, okay, and we have got a coolant here, okay. And in order to minimize the loss also, okay, we don't want to have too much of loss, because we are channelizing the energy that is being generated from here. We do have something which we also call as the reflector. But then, as I said, it's not as simple as it looks. It's just a schematic. The electronics is not involved here, okay. So this is how basically a nuclear reactor, and this is something which you have already seen. Probably I won't even ask you a question on how a nuclear reactor works, okay. The question will probably from the next one. So a very important part is the nuclear fuel. Okay, so let's just talk a bit about fuel, the technical details of nuclear fuel. Okay, so we'll just go to nuclear fuel now. Now imagine you have uranium, and as you might have heard about these term abundance. Now, abundance is something which is there in your lower class also. You might have heard about something which you call as abundance. Okay, so when we talk about something like abundance, it means that what is the availability of that particular element. And if you look into the abundance of uranium 238, it's far more compared to uranium 235. What do you mean by that? It means that you have a ore of uranium. You have a ore of uranium. It's not that it will have only uranium 235, right? You cannot have a ore of uranium 235 and 38 separately. So it will basically have a combination of uranium 235 and uranium 238. So I need uranium 235. That means I have to separate out uranium 238 from uranium 235. The abundance of uranium 235 is only 0.72%, and uranium 238 is 99.275%. If you want to separate completely uranium 235 from uranium 238, well, that's a very, very difficult job, okay? So usually we don't do that. Okay, so what we do, are going to come to that later. But then you see, uranium 235 is a fissile material, and uranium 238, as we have seen from our previous explanation, is a non-fissile material. Okay, so in non-fissile, we may say that the cross section is very less. Okay, the chances of having a compound reaction, okay, will be less. The chances of the Q value overcoming the activation energy is less. So the probability of having a reaction will be less. But when we talk about uranium 235, a slow neutron can easily set up a fission reaction. Okay, and for this purpose, most of the time, for any kind of fission reaction, uranium-235 is considered. Now the thing is, if I have some amount of uranium and most of it is uranium-238, then me having a chance of a fissionable reaction is less. So what do I need to do is I need to reduce the amount of uranium-238 there. Okay, uranium-235 will be there, and I have to do some chemical process so that I can reduce the amount of uranium-238. Okay, and this process is something which we call as enrichment. Enrichment is the term. Okay, so just look at to the term now. That is important. Okay, so we are talking about enrichment now. So see, this is one of the
सर ये
easier
प्रोसेस
topics.
फिर से थोड़ा बोलिए.
So I'm explaining.
Enrichment.
Yeah, it's not over. Okay, I'm explaining enrichment now. Okay, so see, so the basic logic is that uranium 235 will be lesser in amount compared to uranium 238 in the uranium ore, okay, or the uranium ore that basically it is mined from. Okay, so you know, even in northeast we have it. Okay, in fact in my state Meghalaya also it's there. Okay, so it's available, but then extracting it from the ore possesses other threats. Okay, but we are not looking into that, but we are just looking into the ore and how to derive more uranium 235. So if we consider something like uranium 235, and let's say it is not 0.75%, if I have an amount of let's say 0.1 gram, and out of that 3 to 4% is uranium 235, I will say that it is enriched. What does it mean? It means that I have got more uranium 235. So imagine having a block of uranium, and out of that if you have only 3 to 4% of uranium 235, still you can generate enormous amount of energy. That is how radioactive uranium 235 is, and that is why radioactive elements comes under a very big threat for the environment. Okay, even for the living beings around. Okay, it's that's why like reactors and all are always constructed in a place which is far away from the city. Okay, it's very important. So you know, in general, even if you consider something like a transformer, okay, which basically gives out the AC power to all the households, okay, in a city, basically that should also be constructed far from the city. But nowadays it's so much crowded everywhere that it's really not possible. But you know, these things are also harmful. So if a normal AC power generator is harmful to you, this is a nuclear reactor. It's a harmful on a different level altogether. Okay, so this can be easily understood from this. Even if you are having 3 to 4% of uranium 235 in let's say 0.1 gram of uranium, that is enough, enriched enough. Okay. So how do you do that enrichment? It's simple. We are not reducing uranium 235. We cannot increase uranium 235 also, not possible, because you are extracting it naturally, and whatever amount is there, it's there. You cannot add more to it. So what we do is we do chemical process to remove uranium 238 from there. So imagine you have removed uranium to 38, 80% of it. Okay, it's very difficult to remove every uranium to 38. Okay, every atom of uranium to 38, not possible. Okay, you have restrictions. Okay, in terms of the experiment or in terms of the chemical reaction that is happening. So if we do that, we just have 19.3 units of uranium 238 available now. So if we are considering 20 units, in 20 units, 19.3 units will be nothing but uranium-238, and 0.7 unit will be nothing but uranium-235. And now if you work out the maths, you know that in this block you will have more uranium-235 now. Of course, not more compared to uranium-238, but individually it's 3 to 4% now. And that is enough to cause a nuclear reaction, fission reaction, to generate energy in a nuclear reactor. Okay, and that is called enrichment, and this is around 3.5%. Okay, usually, typically, so 3 to 4, 3.5% enriched. Okay, so this is what is done usually to have more of fuel. Okay, more of fuel. If you look into the nuclear reaction, we are not really going to talk about how to reduce uranium to 38. Okay, we're not going to look into that. But this is what is enrichment is all about. Okay, so this is important to understand, because this is something which we might not have come across before. Okay, next let's go to the topic of moderator. Okay, and let's see what additional thing we can learn. So there is a bit of maths here. Okay, man, this is very simple. We have a moderator which we actually use to slow down the neutrons for the nuclear reactors. So what happens is if the kinetic energy of neutron is too high, we can actually reduce it. Okay, and this can be actually done by elastic scattering. Don't get confused here. The elastic scattering happens in the moderator. That means heavy water, not with uranium. Okay, there if elastic scattering happens, we are not going to get any kind of fission reaction. So please don't get confused and write confusing answers in your exam. Okay, so we have a neutron which is coming, and it will have some velocity v, and we have a moderator which is at rest. So it's not moving around, right? And as soon as the neutron hits, there will be a kind of elastic scattering. And if we consider the extreme limit in an elastic scattering, all the energy from the neutron will be transferred to the moderator. You know, we need thermal neutrons here. So thermal neutrons are slow neutrons, really slow neutrons. Okay. So for practical purposes, we can say that this is an example of elastic scattering. Okay, so that means whatever energy was there, okay, let's say if we consider this initial momentum of not energy, momentum, initial momentum of the neutron will be equal to the final momentum of neutron, okay, plus the final momentum of the target. So the target is nothing but the moderator material. So that means the atoms of heavy water. Okay, so we also say that if we consider an elastic scattering, that this v, okay, which is nothing but the velocity of the neutron, is v2 minus v1. Okay, or what we can say about v2. What is v2? V2 is nothing but this. That means the velocity of the target. So velocity of the target, if you look into the equation, is nothing but v plus v1. Okay, v plus v1. What was v? V was the velocity of the neutron, okay, and the velocity of the neutron after scattering is v1. Okay, so this is the total velocity v2. This is what is elastic scattering is all about, right? So if we talk about mv, we can just replace the values here. Okay, we're just doing a limiting case here. Okay, so don't worry about it, it's a limiting case. The mass into velocity is equal to mv1 into m, capital M, mass of the moderator, into v plus v1. V plus v1. You can just replace it. Okay, and then if you do the maths, we can write down what is the velocity of the incoming neutron. So you see, if you understand this relation, you can actually identify the velocity of the incoming neutron. Okay, so it depends on what is the mass of neutron, what is the mass of the moderator divided by m plus m. Okay, so I am already giving you an example beforehand that okay, the moderator is heavy water, the incoming particle is neutron, but this is not the case. Okay, in general, initially when scientists or people try to understand that what kind of moderator can be used in a nuclear reactor, they did this calculation, and then based on the mass of the atom, they said that okay, heavy water should be a good example. Then they used heavy water, and then they found yes, the nucleon or the neutron slows down further. Okay, so what happens is if basically if you look here, if this mass of neutron, okay, is let's say this m, small m, let's say not, it's not neutron, it's any mass m. If this is greater than capital M, okay, so you have got a value here. If this is the case, okay, this v1 will actually become negative, okay, for lighter particle. So for lighter particle means if this particular m, that means we are talking about neutron now, let's say, is small m, and the mass of the heavy particle is, let's say, the heavy water. So we have got a small value subtracted from a larger value. This v1 is going to be negative. So that means if we have a lighter particle incident on a heavy particle. Okay, this is the maths. Okay, simple thing here, not very complicated. So when this happens, that means a lighter particle will hit a heavier particle. We basically have a okay. So if a lighter particle, that means let's say neutron, hits a heavier particle, that means the moderator, we are expecting uh, more or less an elastic scattering, more or less an elastic scattering. Okay, and we basically have all the energy of the neutron transferred to the moderator, as a result of which the velocity of the incoming neutron will reduce and it will be a thermal neutron. Okay, if we actually consider the final kinetic energy of the neutron, okay, you know this is half mv square. So half mv square will give you the kinetic energy, which is the initial kinetic energy, and if we just replace this v1 here, this term will come in, this term will come in. Okay, so obviously this term can be negative, but you know kinetic energy cannot be negative, right? The kinetic energy cannot be negative, so if there is a square term, the kinetic energy is not negative. Okay, but you know this is m minus m divided by m plus m. So you are subtracting a small value at the numerator by a larger value at the denominator. Okay, as a result of which this entire value will be less. So, okay, so that means the final kinetic energy will be lesser compared to the initial kinetic energy. That is the meaning of this mathematical expression. It's simple. Final kinetic energy, what is the final kinetic energy? Half mv1 square. What is the initial kinetic energy? Half mv square. So if you see this, this says that the kinetic energy is reduced. This is a simple example of elastic scattering, okay, which you might have done in your class 12. But you see that this is also applicable here. Okay? So this is what is the work of a moderator is all about. So we definitely have some concluding lines here. Lighter is the mass of the moderator material. Okay, lighter is the mass of the moderator material m compared to the mass of the neutron. The reduction in the energy will be more efficient. Now this is actually for conservation of linear momentum. Okay, so it's not that this mass of the moderator will be too heavy. Okay, if it is too heavy, then practically every energy is transferred to the neutron. The neutron doesn't move ahead. So if it's so heavy that it does not allow the neutron to move ahead, there are no chances that the neutron will go and hit the uranium target. Okay, so there has to be a balance. Okay, so if it is lighter compared and the mass of the neutron, okay, the slowing down process is more efficient, in simple words. Okay, so if you consider like proton and neutron, they are light. Okay, so we can put water as a moderator. So you know water will basically have this 1h, and it will hit the neutron and it will basically become 2h. So there is also a possibility that some of the neutron might get lost in the moderator. Okay, so this has to be efficiently done. The complication here is that the neutron that comes in should not be too slow. Okay, so that is also there. So what does it mean? It means that in many cases, okay, the neutron might get lost as it will be absorbed by 1h to become 2h. Okay, so the aim is not to reduce the number of neutron, the aim is to only reduce its energy. Okay, so that's why if we are having an incoming neutron, you cannot have too slow a neutron coming in. That has to be having some kind of kinetic energy so that 1h does not become 2h. Okay, so that is important. After the neutron has been slowed down, 238 can easily absorb the neutron. Okay, so we don't want the neutron to get lost. Okay, so that is also why the energy of the initial neutron is important. Okay, but then this line you can ignore. I think this line I've explained it number of times. Even if you don't write, it's fine. Okay, what is important is what should be the property of the moderator. What should be the property of the moderator? The moderator should actually have a low z value. Okay, the moderator should actually have a low z value, so the number of protons should be less. It should have a low cross section for neutron. What do I mean by this? If I have a high cross section, then the neutron will get absorbed. The reaction will happen. So it should have a low cross section for neutron. That's the technical term that we use, right? Of course, low cost. Heavy water is low cost. Okay. Any experiment we are usually looking in for low cost. Okay, and easily available. So heavy water can be easily made. Okay, so that's easily available. Okay. And finally, the third element is the control rod. Okay, so what did we see is nuclear fuel, that is important. Okay, and then we talked about the moderator and the control rod. But control rod, I'm not going to go into the detail. Okay, it's just this much. Okay, this much, and we kept it very simple here. So that actually ends your topic of nuclear reactors. So nuclear reactors, I'm not explaining nuclear reactors here. I'm just trying to throw more light on what is the use of this materials, okay, the control rod, the fuel and the moderator, specifically on fuel and the moderator. So control rod, you know, it is cadmium, which is a very good material, okay, because it can absorb neutron, okay. The nuclear cross section for neutron in case using cadmium is more, okay. So it has got a large absorption cross section, and that is why cadmium is used, okay. So if there are excess neutron, which will happen if you are considering any of the fission reaction, there are either 2 neutrons or 3 neutrons coming out. So if there are 3 neutrons or 2 neutrons, you need to grab 1 neutron or 2 neutrons out of those 2 or 3 neutrons so that it does not move ahead. So we use cadmium, and it has got a large absorption cross section. So that's the technical word. And it absorbs neutron in case excess of the same are available, okay, to control the reaction. So that is basically used to control the reaction. But this is something which you might have already known. So nuclear reactor basic is already known to you. Control rod is already known to you. What I've introduced in today's class is something extra for the nuclear fuel and the moderator. Okay?